Hello, the topic that we have is generalization. The team is Jairo Castrellón, Diego Vega, and me, Sofia Murillo. We have a quote for you about overfitting. This presentation shows an usual problem with machine learning, which is how to choose the best model to fit the data. Here we present underfitting and overfitting problems with the training and test data sets and how generalization can be used to prevent those problems.
The goal of the presentation is to give a more formal concept about what underfitting and overfitting are. We are going to give some examples in different machine learning models like classification or regression. Therefore, we're going to presentate generalization as a tool to correct overfitting on training models and to build the best test model. From the beginning of machine learning studies, the biggest problem had been to choose the best model that fit the data. Lots of procedures have been used to prevent error on the model predictions. That errors are usually called overfitting and underfitting. Two concepts that we are going to define in this presentation, which basically tell us if the training model are worth fitting or not. Doing that with the error analysis on the training model. Another thing which we are going to talk later is the test data and its test error. That indicates how well the classifier or model will perform on new data. This is known as generalization. If the model generalizes well, then it will perform well on datasets then that are similar on structure to the training data.
Well, an important question that we can formulate for ourselves is how can a machine learning model make accurate prediction on data that it has not seen before? Well, the answer is generalization. And this is the capability that we seek when we apply machine learning to challenging problems. And we can formulate three questions. The first is what is generalization? Generalization refers to how well the concept learned by a machine learning model applied to specific examples not seen by the model when it was learning. But why generalization is so important? The goal of a good machine learning model is to generalize well from the training data to any data from the problem domain. This allows us to make prediction in the future on data the model has never seen. And third, how we know is if our model is a good model. In machine learning, when we talk about how well learn, a machine learning model learns and generalizes through new data, we have to talk about overfitting and underfitting. That are the two biggest cause for poor performance of machine learning algorithms.
There are two problems that we have for solving with generalization, underfitting and overfitting. Overfitting refers to a model that fits the training data to what. Overfitting happens when a model learns the detail and noise in the training data to the extent that it negatively impacts the performance of the model on new data. We have two cases. The first case is classification. Um, in classification, we try to meet the and fit the data. Then we have the regression, and in regression, all the points uh, joined between them.
The problem of underfitting in a model is that we have a model that is not suitable for the data that we have. It will be obvious as it will have poor performance on the training data and eventually in in the predictions. Here we can see a regression model where our training data it has a prediction of a straight line, and we can see that there are some points that are too far from the line. So the training error will be high, and the prediction error will be high too. And for this example of classification, we have the same problem. The model is maybe too basic or too simple for the data. So maybe by make it more complex, we could have a better prediction of the data.
Well, now we are going to talk about an appropriate fit. Ideally, we are looking for the midpoint between underfitting and overfitting. Uh, in the same example than before, we have the classification problem and regression problem. Notice that here in the classification problem, the model are not as simple as underfitting and are not as complex and than as overfitting. For example, here we have two red points in the blue field. Um, and here we have some layers that are not in the red line. That could be an optimal model. To understand the goal of select the best model, we can look at the performance of a machine learning algorithm over time as it is learning a training data. In machine learning, we have two phases: training phase and testing phase. Training phase use the training data to build the model. With that model, we can do the testing phase. With the testing phase, we use the test data that we are talking later about the test data. Okay, when we have the test data and the model, we can apply the model for that test data and look for the results. Well, over time, as the algorithms learn, the error for the model on the training data goes down, and so does the error on the test dataset. Here, for example, we are looking a graphic that are comparing the model prediction error and the model complexity. Notice that when the model complexity is low, the model prediction error is high for the prediction error and the training error. But when the model complexity is growing, the model prediction error are decreasing, and when the model complexity is growing more, the training errors are decreasing, but the prediction error are increasing. Then we are looking for a model complexity uh, that are here in the intermediate of the complexities. Well, now the importance of generalization is the generalization error, because, for example, here we was talking about the errors, but how compare all that errors? Intuitively, generalizations means that you predict well on unseen examples, have low expected error, in other words. Here we have the formula for the expected errors, where V is denotes a loss function, and P of X and Y is the unknown joint probability distribution for X and Y. That is the expected error. Generalization error, or the out of sample error, is a measure of how accurately an algorithm is able to predict outcome values for previously unseen data. The generalization error is the difference between the expected error that we had before and empirical error that is here. In other words, the generalization error is defined as that rest. An algorithm is said to generalize if the limit when n tends to infinity of that difference is equal to zero. Okay, now we are talking about validation. Here we are looking the split of the data. In the beginning, we have the training data, another set that is the validation data, and another more small test data to predict the future data. The standard approach to supervised learning is to split the historical data into training, validation, and test data. But what is training data, validation data set, and test data set? Well, training dataset is the sample of data used to fit the model. The actual dataset that we use to train the model, in other words. Validation dataset is the sample of data used to provide an unbiased evaluation of a model fit on the training dataset while tuning model hyperparameters. The evaluation becomes more biased as skill on the validation dataset is incorporated into the model configuration. The dataset is used to evaluate a given model, but this is for frequent evaluation. Um, uh, we use this data to fine-tune the model hyperparameters. Okay, and the test data is the sample of data used to provide an unbiased evaluation of a final model fit on the training dataset. The test dataset provides the gold standard used to evaluate the model. It is the only used once a model is completely trained. Well, but the principal question here is how we can select the best model. Good practice dictates that the model only see the training data during learning, and the result of the model are compared based of the predictor for the validation data. The model giving the best validation result is select as the best choice. There are many ways to select the best model. Sometimes we can use a k-fold validation, or in algorithms we can use some libraries like stacked generalization. But for that we going to watch some examples later.